Well, I've known Professor Manas Mukherjee for a very long time. Actually, almost 25 years to date. I mean, just a few days short of 25 years. So it was in 2000, August, that I met him in Bangalore at the Indian Institute of Astrophysics. And the very next year, he, I think, made a very wise decision to join an excellent group on trapped ions at GSI in Germany. So he got his PhD there, informally from University of Heidelberg, but his work was done at GSI, which is the German Center for Heavy Ion Research. And there for his PhD, he did what I would consider as some very important work and on using penning trap. I don't remember all the details, but terms like ship trap, ISO trap come to mind, and I remember a lot of very important work that he did at that time. In particular, I think it was the mass measurement of magnesium isotope 22, I guess, I think, which was a ERL paper, but he published a lot of very good papers at that time for his PhD. He was using the penning trap, as I said, for mostly measurement of masses of rare isotopes. And then after completing his PhD, he went to the University of Innsbruck in Austria, where he joined a world-renowned group on trapped ions led by Professor Rainer Blatt, and he did outstanding work there as a postdoctoral researcher. And after that, he returned to India and worked for 4 years here. I mean, not our center, which was not there at that time, but the Indian Association for the Cultivation of Science, where he set up a very good lab on trapped ions and started some very interesting work. And 4 years later, he got an offer from the Center for Quantum Technologies in Singapore, which I guess he could not refuse. And so he took up that position. And, in those, at that time, CQT was one of the world's leaders in quantum technologies. They did pioneering work there. It's still a leading center for quantum technologies. And so Professor Manas Mukherjee, I think, now holds some 3 or 4 positions. He's a principal investigator at the Center for Quantum Technologies. He's an associate professor in the physics department. And he holds 2 more positions at A-STAR, which is a leading research center in Singapore. He's the director of the National Quantum Fabless Foundry. Is that correct? Okay, yeah. And also the head of quantum technologies and engineering. So as you can see, he's the most powerful man in or person and scientist in quantum in Singapore. And I mean, one thing that has always impressed me about Manas is his choice of problems, which have always been very important and interesting, covering a lot of areas of quantum science and technology. And I mean, one of his latest interests is on quantum machine learning. He's going to be talking about that today. And, we should be grateful not only for the talk he's going to give us, but I mean, all of us are here because of him, not just for his talk, but it was he who proposed this idea of secure Center for Quantum Engineering, which was accepted by Dr. Punyendu Chatterjee and our board of directors. And that's how, Secure came into existence. It was to a large extent, Manus's brainchild. And so today we look forward to hearing his talk, and I'm going to extend an invitation to Manus to come and visit us. I mean, I know you're very busy, but still, I mean, you can afford to visit us at least once a year. Okay, so with these words, I mean, I'm going to request Manus to give his talk.
Thank you, Professor Das, for the generous introduction. So I believe I will get an extra 7 minutes. So let me, so I believe I'm audible. Am I audible?
Yes, sir.
Can you hear me?
Yes, 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 yes.
Perfect.
Yes, you are.
Wonderful. Okay, so maybe a bit of correction. So actually, since April, I moved from A-Star and I'm fully at NUS CQT. We are starting a new program on quantum processor initiative, and I will talk about it at the end of the talk. But again, for today, what I am going to discuss with you is a research topic we have been working on for the last couple of years, is quantum machine learning, and try to apply those into the real experiment with trapped ions, that the setup we have at NUS. Maybe I should also mention that most of our research fund comes from the National Research Foundation and under the quantum engineering program. It's kind of similar to the NQM in India. And here we are mostly interested in development of trapped ion-based quantum computer, at least from our group. Okay, so the broad topic is about machine learning, right? And machine learning, of course, we know we are moving very fast. Today, half of our daily work, I would say, at least for me, I don't need to think much in writing maybe a student recommendation. AI helps me a lot. Yeah, so nothing to maybe it's a time that we think about how we can use quantum also as a resource for learning. And this we can divide in several or maybe 4 quadrants where we can take classical data and use classical machine learning, or we can take classical data and use quantum machine learning, or else we could take quantum data and use classical machine learning. And the last one is quantum data and quantum machine learning. For today and most of what we do currently, it is the classical data and quantum machine learning. I will touch upon a little bit about quantum data and classical machine learning just in one slide that we have worked on. So with that, this is the main group, but this is a bit dated. There are new people in. While the main work that I will talk about was mainly pursued by Torun, who is now in University of Hyderabad. Then Alex. Alex is actually our in-house computer scientist. His background is a master's in CS from UC Berkeley. And then Jasper, who has just submitted his thesis. Okay, to start with, maybe we should also talk about why we do it. As you know, that we are currently lacking a good quantum machine which can solve Shor's algorithm, or for that matter, any practical problem. So it's a big issue to actually know what problems can actually be solved by quantum machines, at least in the near term. Why is that? Because the current machines are noisy, and these are called noisy intermediate scale quantum machines. So which means that these noisy machines are not able to provide solutions which we can rely on. Yeah. However, there are certain types of algorithms which are mainly based on parameterized quantum circuits, which kind of a variational types of algorithms, which could, or it is perceived that these could be of some advantage. We, however, do not know or do not have any guarantee for these. Of course, you can look into some of the review articles which has recently come up, including the last one, which is a benchmarking that was done with the existing machines that you can get from either a commercial vendor or from university labs. And what is shown here is along the x-axis is the depth of the circuit, along the y-axis is the number of qubits or the width of the circuit. The color coding here is the fidelities that you get for different algorithms. So one thing is clear that based on algorithms, you would see certain whether it is a depth dependent or it's a width dependent algorithm. And the red here means that it is unusable. So the fidelities goes below 0.5 or even to 0.2. What this means that at present, the number of qubits, that means the width or the depth of the circuits are not large enough to do anything meaningful, which we cannot do in a classical computer. However, given the hope that maybe if we could improve on the depth or the width, even with these noisy machines, we could do some useful algorithms like quantum chemistry or maybe optimization or quantum machine learning. Now, all of them has one thing in common. These are parameterized circuits where the parameters are fed into the circuit, which are then optimized to provide you with a optimized cost function. Some form or the other, all three has the common baseline. In principle, we can do different types of quantum machine learning algorithms. However, our current interest lies in classifiers. So what our current interest is to develop quantum classifiers and to see if they can provide an advantage. Now, here, when I say advantage, it might come in different ways, and I will discuss as we go along. And the choice of this particular problem, that is a classifier, stems from various reasons. Actually, a classifier and a regression are not two different things. So you can see its application can be from digitizing handwritten documents. It can be predicting the stocks, or it can be predicting the results of an election. Or it could be an early detection of disease by image classification. I will not talk about any of these. However, I will provide you some general understanding of when we apply these, what kind of problems it could be used for. And maybe more specifically, I will go a little bit into the top corner where handwritten documents could be deciphered or can be digitized using a quantum machine learning algorithm or a quantum classifier, which can also be done by a classical CNN. So we will show some kind of a comparison between those two. And our current interest, which I will not cover, but we are currently working on, is more on the early detection of diseases. Of course, here it is shown in terms of leaves, which are getting some kind of a patches, which indicates there is some disease being developed. You can go actually deep down and look at the cellular level as well. And that's where we are interested in. Okay, what does classification in short means? Let's say I have data and I have one parameter X, and it is told to me that there are some orange dots or some blue dots. Right? Now, one, I can call them a class A and the other one class B. But however, if I do not go to a higher dimension, I don't see them separated out. And if I do see them separated out, I have to find the boundary which separates the blue from the orange ones. This can be achieved by different classifiers, the classical, like SVCs, the neural networks, convoluted neural networks, or deep neural networks. Now, all of these could be implemented nowadays quite easily on any kind, even on a laptop. Yeah. However, the question arises like, is there a difference between those classical machine learning architectures compared to the quantum one? Now, if you go through this article from Jerby and his team, you would see that, in fact, broadly speaking, okay, number one, the problem is any kind of quantum classifier or quantum machine learning problem. First of all, there are different types, and it is not easy to actually compare them because of their underlying models that are used. The second is, if you compare between the different quantum machine learning algorithms, you cannot compare them easily with the classical algorithms. So it is also not very easy to quantify if there is an advantage. So that's one of the major problems in this field. However, what they have done is that they have come up with unified architecture to classify the quantum algorithms into either implicit models or explicit models. Now, what does implicit and explicit means here? So one possibility is that you can parameterize your data into some parameters of your circuit. Then you define a variational parameter which you optimize, and you label the variational observable. So this way you can call it an implicit model. The explicit model would be the kernel types, where you actually map your data, classical data, into the parameters in the Hilbert space and perform projections between different axes in the Hilbert space. And then finally, you label your final outcome as the level on some of the basis in the Hilbert space. So that would form the explicit model. Now, both of them actually can be, in this paper they have shown, this is all theoretical work, that both of them can be shown to be linear quantum model. Now, once you do that, you will find that there is one issue, which is either you can see the implicit model is the kernel model, explicit model where you have the feature encoding and the variational measure. The data re-uploading, which is more recent algorithm, this actually do not fully fall into either implicit or explicit model. So the question therefore comes is that mostly whether the data re-uploading algorithm would have some advantage compared to the other two, or the other question could be asked whether the data re-uploading algorithm could have advantage compared to the classical machine learning algorithms. Now, according to them, you can see in terms of the resources. So there are two theorems, which the first one, which is the representer theorem, which says that the implicit models always have a lower labeling error. And this was one of the reasons why a lot of work has been done on the implicit models. However, what was not being shown was how much of resources, both in terms of qubits as well as in terms of data, are required actually to train these models. The second important theorem is the universal approximate theorem, which tells you, and this is a very classical theorem, which tells you if you have an infinitely large number of nodes in a CNN or even a neural network, you can actually write down any function with that nodes. What turns out is that the data re-uploading algorithm, which I will discuss in a few minutes, also follows the universal approximate theorem, which means you can use a single qubit and multiply load it with the data as well as the parameters. And as it rotates in the Hilbert space, it will convolute and can describe any function. So this is a very powerful tool which gives you actually an exponential advantage in terms of the number of qubit requirement, in terms of resource. In terms of the data points, it's as good as the explicit models. Okay, so now goes to the actual implementation. So we implemented this on an ion trap qubit, and I will talk a little bit about the basic requirements for a qubit. Probably this is for younger audience. Then a comparative performance of these qubits, and then I will talk a little bit about the stacks that are needed in order to implement such a quantum machine learning algorithm. In general, qubits can be formed from any quantum systems which has multiple levels. You can choose your favorite two-level systems, and then it forms a qubit. Of course, it has to have these 5 important criterias, which are not too difficult to fulfill. And this is done in atoms, in molecules, in photons, or in microwave photons. And we call them superconducting qubits, or in case of atoms, either an ion trap or an atomic tweezers. Currently, you would see these are typical numbers that you would see in terms of the performances. Of course, these are changing with time. This is, again, quite dated. The atomic qubits are coming along quite fast as well, which is not in this list at the moment. But maybe for the younger audience also to note is that the NMR was one of the pioneers. And at present, by all means, we know that NMR cannot be scaled. And therefore, this has dropped out of the race. Topological insulators or topological qubits is very notional. And none of the qubit has been shown without any controversy, let's put it this way. But if they do exist and if they are made, they can, in principle, have a very high fidelity and they can be protected. The most advanced ones are the superconducting qubit on the left side. On the right side are the trapped ion qubit. In terms of technologies, you can see there is a big difference between the superconducting qubit, where you need a dilution fridge to go down to millikelvin temperature. On the right side, you can, in principle, work at room temperature. But other technologies you need to heavily here are vacuum, as well as optical technology, which forms the large part of the qubit manipulation. Okay. In our case, we work with 138 and 137 barium ion. And what you see on the left side is actually a real image of the linear chain of ions. Each of them is a qubit. It has, in principle, a qubit in a trap, or an ion in a trap has two state space, if you like. One is its external motion, which is given by a simple harmonic oscillator on the left-hand side. The other one is its internal state. And the internal state of the ion could be many energy levels. But for us, the most interesting one are the S, P, and the D, which forms its laser cooling stage, while our qubit is formed between S and D5 half. And you can see the time if the ion is in the D state, it can live up to 30 seconds, which is a very long time compared to any computation or gate times that you can think of. However, to start with, we do preparations which are called Doppler cooling and sideband cooling. These are names, but what it eventually means is that we bring down the temperature of the ion from first by Doppler cooling to about N, which is the average Fock number, about 8, all the way down to roughly N bar equals to 0, meaning almost the ground state. If you look at the qubit as mentioned, so this forms our qubit. Of course, we work on the Zeeman level, as you can see, -12 to -5 half. And that's a quadrupole transition, which means it's not allowed to the dipole. And therefore, it is a hard transition to actually drive it. We have a laser which is as narrow as 120 hertz on a terahertz frequency. The left side shows the Rabi flops on this, and you can see the contrast roughly remains the same over, in this case, about 600 microseconds or more. We have a heating rate about 20 phonons per second. This is not so important in what we are going to talk about. We have gate fidelities, which is given by this curve here, which goes to about 0.5 after 30 pulses. Then the fidelities for single and 2 qubit gates are roughly given here. The first part of the applications that I will talk about is the implementation of classifier, and this work is done in collaboration with Jose Ignacio and his team. They are also the proposer of the first algorithm on data re-uploading. So how it works is you can think of the quantum computer to be made of 3 stacks. The lower stack is called the physics package, where the ion trap stays in the vacuum. Then you have a middleware where it is a low-level control over the whole experiment. And then on top, you have your algorithms, which runs on a CPU. But of course, in these kind of algorithms, what happens is that the physics package provides you the value of the cost function. Then the CPU does the optimization, which is a classical optimizer of your choice. The parameters are then fed from the CPU down to the middleware to go into the physics package to provide the new cost function for optimization. And because you have a tandem play between the classical and the quantum computers, it is called a hybrid algorithm. Of course, this hybridization can be done at different levels. In this particular case, I'm talking about the hybridization at the CPU and the quantum level. You could do it in the middleware, and then it becomes much faster. But however, for our purpose, it doesn't need to be fast, because only when you have a cost function, then only you need to run the optimizer. So it's rather slow. Now, how it works is the following. Once you have an optimal parameter, you perform some multiplication with any random data. Then if you run the classifier in your quantum machine, it will create a class A or class B depending on your data. So in our case, to simply think of a binary classification, you would like your data of class A to all reside close to the North Pole, while all of class B should reside close to the South Pole. And you maximize the distance, and therefore you can classify the data accordingly. Now, one thing which I have not shown here is that you can only do this if you already know the optimal parameters. To know the optimal parameters, you have to train your system. And if you look into the literature, in most cases, it is very hard to train current NISQ machines for any VQA kind of problem. And the reason being, the NISQ machines also have drifts. So as you go along training it, it would also move the optimal point. In full, if you do an optimization, it would look like this. You will start with a classical optimizer, which will provide you with some variational parameters. Your data are then multiplied with them, put into some gate parameters, which are, you can think of rotation in the Hilbert space. And then after that, you do projective measurement. After the projective measurements are done, you know the levels of the data, and then you find the cross entropy or the cost function. Then you feed it to the classical optimizer, and this process runs till you find the optimal value. Okay, then what kind of ansatz you want to take, that also depends on your problem. In our case, for binary classification, we looked into the state of what kind of rotations you can apply, and you see, depending on the ansatz, you may explore the whole space that you have, or you might not be exploring many of those depending on the ansatz, which just tells us that the ansatz that you take out of these 4 is very important. Now, once you do everything correct, you could actually get your test accuracy down to 0.05% and 2 qubit to 5%. Then you can achieve about 98% algorithmic accuracy on this. We have also performed both supervised and unsupervised learning, which shows us a difference about 2%. And this is what it is. So if you perform an ideal case scenario, your optimized value should be here, but in the experiments, you would find the optimized value, the red dots. So this is published in 22, and then there was an experiment by one Japanese group, and they have performed a very similar experiment. That's the result from their experiment. And they could achieve a binary classification of the order of 95%. So we moved on to training the system. And this is one of and our motivation to do training is to see if the current NIST machines are able to train if we do not prompt them what the optimal values are. And we have used a few different optimizer, like the genetic algorithm or the gradient-based algorithms. What you see here is, generally speaking, the genetic algorithms perform better compared to gradient descent algorithm. Now, one might wonder why, because generally speaking, gradient descent is a good optimizer. Now, the reason to see such a behavior actually is somehow here. So if you look into the parameter space, we have large number of minimas in the whole space, which means with the NIST machine, if you try to do gradient, which the errors are high, it will remain stuck at 1 minima and would not move out. There are ways to move it out, but then it takes longer steps. And once you take longer steps, you can't find a minima. So therefore, the GAs are performing way better. And what you see on the right side is how would an experiment would look like. As the accuracy increases, you start to see the circle being formed inside. Okay, I'm switching gear to some other topic which interests us, is the vulnerability of hybrid system. Now, what does it mean? As the quantum system scales, we know that there would be cyber attacks on them. Now, the cyber attacks in this case is more complicated. You have different channels. It could be attacked from a classical channel, which is the easiest. It could also be attacked from the quantum channel. And in this case, our collaborators are Anupam and his group from NTU. And first, I will talk about the classical channel attack. And this is quite simple. So this is again the same circuit that I showed before. You have a classical processor which does optimization, and then a quantum processor which does the cost function evaluation. Your side channel attack in this case happens at the optimizer. So you feed in a malware in this case, and that is one of the first malwares, perhaps in the which were attacking a quantum computer. And you can see as the noise level increases, the accuracy drops to 50%, which means basically it's noise. Now, of course, such a kind of thing where you do a kind of an attack, even though the problem itself is not very difficult, it's a classical malware. It was done to infect the tools that produces the RF generations in our experiment. So in a way, it is not that difficult to produce the malware. But given the fact that it is so vulnerable, actually the student got also a student's award in QCCS last year. What is more important or interesting for us is actually to look into where you have a quantum channel of the attack. And this is where adversarial attack comes in. What it means is that our classifier can classify numbers which are handwritten like this. Now, if you look carefully, this 2, this is also a 2, which may look like, I don't know, alpha, but the machine has to distinguish between this 2 and that 2. Now, you can think of noise in the image as well. Now, you can also think of engineered noise in the image such that I change the 0 with certain small amount of noise, minimally put in, so that my machine is wrongly trained to see this as 1. So our collaborators from NTU would actually do the attack, and our main reason to perform the experiment was to see that if quantum, particularly the data reuploading algorithm, provides a robustness against such attack as compared to any classical algorithm. The first simplest way is a PCA, but PCA again is not. PCA is principal component analysis. In this case, you would put it in along the principal axis, and then you can classify the zeros and 1. In this case, a binary classification. However, if you put a little bit of change onto the image, then the PCA is not anymore distinguishable. And the changes we are talking about here are given here. Some of the data that they produced is the predicted value is 0, while the actual value is 1. You can see by human eye, you can call it a 1, but the machine, without any further adversarial robustness, it sees it as a 0 instead of a 1. What we have come up with, which is called a quantum convoluted machine learning architecture. In this case, you actually take the image instead of doing a PCA. You take the numbers of this pixel and then use it with some parameters on a unitary gate, and you keep combining the neighboring ones and then adding some weight, you add them up. So this would work more like a KAN rather than an MPL. And what we have seen here is that if we do that, then what was previously 98% without making any changes, it would, after adversarial, it reduces to about 54%, almost to the, we cannot distinguish. Yeah. However, when we perform the QCNN, and then we can retrieve back to 94%. And this is kind of the results that you can see, that after the CQC architecture, you can keep it, even the test accuracies are of 92% on the experiment itself. It drops down after the adversarial only by 4%. Now, if you do it with PCA, of course, this drops down to something which is a noise level and cannot distinguish. Okay, so I think I have told you mostly about this quadrant, which is classical data and quantum machine learning. I will only spend one slide on quantum data and classical machine learning. In this case, instead of using this half of the optimizer, we used a CNN. And if you use a CNN, you would see that indeed for fixed initial parameters, the CNN could achieve, but still it's about 85%. So it's not as good as distinguishing quantum data as compared to what we have seen on a quantum machine learning. Okay, with this, I would come to the last section, which is about the scaling. Of course, we intend to scale up our system. And in this case, we are moving towards slightly different approach. Instead of qubits, we are looking into, because the atoms come with a large number of levels, which allows us to have qubits. Now, if you look into the scaling of qubits, for n qubit, it would scale as 2 power n. If you have m qubits, it would scale as m power n. And the reason to scale this way compared to 2 is not really the M power, but what we are more interested in is that can we resource efficiently perform error correction onto one system? In general, the more entangling gets you do, the lower is your fidelity. So our main motivation is to perform in a higher dimensional single unit the error corrections and then perform the entangling gets. We are still far from there. At the moment, we are benchmarking our system. On the left side is a CHSH experiment. And what you see here is it's like a Bell experiment, but you cannot do a Bell experiment on a, or you can do a Bell experiment on a 4-level system, but it does not tell you anything about non-locality because it's the same system. However, what tells you about is the quality of your coherence in the 4-level system. And if you look at to the black line, if you violate, that's where the Bell inequality is, and it is almost at the quantum bound, which is about 2 square root of 2. On the upper side, however, we are slightly worse, and this is mainly because of the spam error increases when you do a 4-level system as compared to the 2-level system. That's more a little more into the details. We have also shown now Grover's algorithm onto the same, and we achieve about between 85% to 95% on different levels of this Grover, and mainly limited by the spam error, particularly the measurement error. Okay, and this is the last video that I will run. Basically, this is where our scaling project is currently happening, started since the April this year. And here what we intend to do is a scaled up version of quantum computer based on ions going up to 50 qubits. And this is fully compatible to HPC in terms of it's a fully rack mounted system. And it would come in 3 or 4 racks with the trap and everything onto a 19-inch rack compatible to the system. With this, I would like to thank you for your it's a little odd with these Zoom meetings because you don't really see. But anyway, please stop and ask me anything you would like to ask.
Any questions? Yeah.
I want. You mentioned something about this malware there. Did you say something about you generate with microwave, or this is just software malware production?
So I cannot hear you.
Oh. Can you hear me now?
Oh yeah, this is good.
Okay. So you mentioned something about the malware there.
Yes.
And is it generated with microwaves, do you say, or is this just an algorithm?
Oh, this is an algorithm. It's really a classical malware which was injected into our control system. What it does is the following. This malware sits and the control system lies on a classical computer. Now, the control system sends out pulses to perform gets. What this malware does is that it changes the level of the RF pulses that we send.
Amplitude of
It
pulses.
injects noise to those RF pulses.
Mm-hmm.
When it does so, it does with a calibrated value. So if, for example, to give you a rough idea, like if you think of these rotations to be, let's say, some in a Hilbert space by some theta, the malware would rewrite the pulse that goes in to apply some theta prime. When it does theta prime randomly, after some time, the test results will be a noise based on certain level of the noise that it injects.
Okay. Thank you. Hello, Manosa. This is Tanmoy.
Hi, hi.
So I have one question. Although this is not related to computation, but more like classification that you have mentioned earlier. So you have mentioned two classes. One is related to class A and class B, that is zero state and one state. Now, my question is, in case of, for example, in case of nitrogen vacancy centers, you have multiple axes. In particular, you have four axes of orientation, right? And then if you would like to do the measurement, for example, the fluorescence measurement, which depends on the axis positions, and then from there, if you would like to incorporate the machine learning there, would it be possible to classify these axial orientation basically from the fluorescence imaging? That will be important in, I mean, if you want to have a fast readout of the spectrum, and then would like to see if you want to reorient your sample for a better count. Yeah.
So Tanmay, is this classical data that you are talking about, or
So
this
yeah, so the
projections
data
of?
comes from the fluorescence data, which will come from the NV center. So this is still classical data, and you are feeding it in a classical machine learning program, basically. That's the idea.
So where is this 4 axis coming from?
So this 4 axis comes from the NV center. So in diamond, there are, so when you create these NV centers, so it depends on the orientation of the NV axis where you are measuring, right? So your magnetic field should
So
be
it's a,
aligned to that,
so it's a
right?
basis.
Yes, that's the basis, right? So where
Oh,
you
okay,
get the
okay.
projection.
Yeah, so it's a basis projection. Yeah, sure. I think you can do it because, I mean, at the end, it doesn't matter. So what you are interested in is the statistics, which separates out into the 4 different classes.
Exactly. Yes.
Yeah, so it's instead of a binary classify, you would do it on a 4-class system. Yeah. I
Okay.
mean, we have done a 4-class system as well, which I didn't show here. Maybe. So yeah, here you see as a 4-class system.
Okay. 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 Thank you. Thank you, Monica.
Yeah.
Okay.
Hello, Manojda. Can you tell me how are you? Sorry, I may have missed that part, but if you are using classical data and quantum machine learning, how you're dealing with the classical data when being fed to the quantum model, the machine learning model?
Yeah,
Sorry, I may have missed that bit.
thanks a lot. Yeah, I was probably very fast.
Okay, okay.
Yeah. So let me go back. I think the easiest place to see this is, so in principle, you can do it at different places, right?
Mm-hmm, mm-hmm.
So
Because quantum
there are,
state preparation is
so, yeah.
very
So
difficult problem anyway. Yeah.
yeah, so the classical data can be fed either to the amplitude of the state or to
Okay.
the phase of the state.
Right.
Now, this is generally what has been done so far. In data re-uploading, however, it is actually fed into the gate parameters, meaning rotational angles of the gate.
Okay. Okay.
So, for
I see.
example, in Hilbert space you want to rotate in any axis, about any axis, right? It's an n-dimensional Hilbert space. Now you have n-dimensional rotational axis in that case. So these n-dimensional data can be fed directly into that rotation.
Okay, okay, all right. Thank you.
I mean, it is, again, if you go by the amplitude or by the phase, it's actually exponential in terms of scaling to upload that. That's a challenge still on
Right.
uploading the classical data into quantum states.
Yes. Okay, thank you. So, I mean, that's what, like, usually, I was just wondering whether converting the classical data into quantum data is killing the otherwise advantage that you're getting from the QML model. So
That's right. That's right.
I was curious. Yeah.
Yeah, that's where the problem lies in both the implicit and the explicit, except the data re-uploading. It
I
does
see,
not fall
I
under
see.
that category.
Okay. Thank you.
Do we when do we expect to see any quantum advantage, quantum classifier?
Well, that's a $1 million question, I guess. I guess your question is perhaps practical applications, because yeah, advantage we have seen, right? But I think it's more about practical applications. I don't know. This is I think the most let's say educated answer. If you think of the applications, again, I would think that if at all we would see advantage, it may not come in terms of speed. It may come in some other ways. And one thing we think maybe in some of the robustness of these systems compared to the classical in terms of vulnerabilities, at least in quantum machine learning. The other place where advantage may come is energy cost, but again, that only would appear when the system is large. I don't think in the small system we would see anything. So those are still areas which are very premature at the moment. It's I mean, it's not easy to actually compare even energetics from a classical machine and a quantum machine because everything is different.
Okay, thanks.
Okay, if there are no more questions, I mean, let's thank Professor Manus Mukherjee again. Thank you very much, Manus.
Thank you.